Good afternoon, everyone, and thank you for joining us on our call today. My name is Nicole Van Wert-Quincy from Transcat, and I'll be your moderator this afternoon. Our webinar topic is 5 ways test tools can improve safety around rotating machinery. The topic is being presented by John Burnett from Fluke. John is a mechanical application and product specialist for Fluke. He has 30+ years of experience in maintenance and operation of nuclear power plants and machinery and other plants. He has worked with customers in all industries implementing reliability programs. He is a certified Category 2 vibration analyst with over 20 years experience diagnosing machine faults and a certified maintenance reliability professional. He has also served in the U.S. Navy as an electrician for 12 years in his past. We expect the presentation today to last roughly 30 minutes, and then we'll answer any questions that have been submitted. During any time of the presentation, you can send questions through the question box to the right in your webinar controls. I also wanted to mention that the webinar is being recorded. You will each receive a follow-up email with a link to the recorded webinar and the slides of today's presentation. At this time, I'm going to turn the presentation over to John.
Thanks, Nicole. All right, so let's get started. And there we go. Just had to figure out how to control this thing. So yeah, so what we're going to be talking about today is we're going to talk about test tools. We're going to talk about rotating machinery, but we're going to talk a little bit about how safety is a factor and how test tools can help us as we look at safety. So we all have heard over the years of the hazards from electrical hazards as well as mechanical hazards from rotating machinery. And, you know, we're all familiar with having our electrical safety PPE, but let's talk a little bit today about the mechanical side. And of course, electrical will pop in there as well. When we think about the mechanical safety, there really are 3 main things that we want to consider. One is to try to work from a safer distance, trying to take machinery offline before a hazardous condition happens. So if we have a machine blow up and parts or hazardous materials fly around, or heat or temperature, you know, those kind of things. And also, let's see if we can use the right tools and think about some ways that we can improve safety. So anytime we're working near rotating machinery with moving parts, we have to do our best to try to keep ourselves safe and keep others safe. So the things we're going to talk about here is, number 1, how to be careful around moving parts. Number 2, how we can work at a distance. How can we stay further away from the danger? 3, using wireless tools and wireless sensors. And then 4, how we can use a vibration meter to improve our machinery so that they're not failing, and we spend less time near rotating machinery. And then 5, how we can improve our machines so that they're not failing and we're in a safer environment. So let's talk a little bit about each one of those in a little bit more detail. So number 1 was being careful about rotating machinery. So pretty obvious that we want to use the right personal protection equipment, safety glasses, gloves, you know, hearing protection, hard hats. You know, we're all familiar with safety. Also, you know, think about you know, necklaces, loose clothing, things that can get caught into it. Over the years, working in vibration analysis with vibration testers, one of the things that, and you can see from these images here, is that when you have cables that you stick in close to bearings of machines to get data, we have the potential of a sensor and a cable getting wrapped around a moving shaft. So one thing that we're talking about here is having breakaways. So you can see that this vibration tester with the long cable has a breakaway cable, and that way if this sensor were to get lodged around a rotating shaft and pull the cable in, it won't pull the tester and you into the machine with it. The breakaway cable is designed to break away. And up on the right, you can see that this vibration meter has a long coiled cable that if that cable were to get wrapped around number one, it's far enough away that you're going to have a little bit, buffer of safety. And also, it will pull that cable out of the bottom of the meter instead of pulling the meter into the device and then parts and pieces are flying around. So let's think about ways that our tools can have some safety features to make them safer. That's one way we can make our tools safer around rotating machinery. Number two is to work from a distance. There's a couple different ways we can think about that. One is we could use stroboscopes, and the stroboscope is something that's been around for a while. We've used so the idea is if we can use a stroboscope, maybe that would be a better thing than using a contact tachometer. So instead of using a contact tachometer to find the speed of a shaft, maybe we can use a stroboscope. Also, the stroboscope allows us to freeze the motion of something that's moving, which helps us find the RPM, but it also helps us find potential problems without getting too close to the machine. So things like, belt slippage, identify parts. So without having to shut a machine down, which we don't want to do because if you shut a machine down, it's not doing its work. But also, shutting down the machine may make things, may cause problems, but using a strobe, we can speed up and slow down the strobing light, and we're able to see moving parts. We're able to identify part numbers. We're able to find damage. For example, we could look at a fan blade and see erosion, corrosion, buildup, also things like moving processes like bottling lines or manufacturing processes. Then we can speed up and slow down and find potential problems that could lead to safety issues or downtime without having to shut the machine down. And all of this can be done at a safe distance. So think about a tool like this to help you find problems without shutting the machine down. A second application of this idea of working from a distance, we talked about the strobing light, but how about just using infrared? So we've probably all heard about infrared thermography, which allows us to see and identify a lot of different things safely from a distance. So electrical problems, we can look for problems with fuse boxes, connections, capacitors, circuit breakers, transformers, all of these from a safe distance. Looking for mechanical problems, you can see that we see down there a picture of a motor. So without having to shut a machine down, without having to actually touch the motor, we can look for problems in the later stages of wear. A machine is going to start getting hot, and so we'll be able to see problems with bearings. We'll be able to see problems with gearboxes, with belts, with couplings, heat exchangers, those kind of things. And then over on the process side, things like tanks and steam traps and heaters and all kinds of things. By looking at its infrared temperature, we're able to detect things like we were with the strobe. Things that were once hidden are now identified, and they can help us locate problems and potential things that are hidden. Number three was wireless tools and wireless sensors. So first, let's talk about wireless tools. So here we see an example of how we could minimize a safety problem by using a wireless vibration, a laser alignment tool. So you can see that by not having the cables, now in this case with laser alignment, the shaft isn't moving, but still having cables for somebody to trip over are in the way. Let's see if we can eliminate some of those cables. It's going to make it much safer. And then another thing we're talking about here is let's minimize the time that we're in a workspace. And because the longer we're in the workspace, the more risk there is that we're going to have a problem. And we do that by having some automated tools that make the process go much faster for us. So you can see this example shows an automated tool in that this laser alignment tool will actually walk the user through. So to make a job that may have taken hours could be done in 15 or 20 minutes because the process is just so much faster. We quickly tag out the machine, we do our quick work, we do our correction, and we get out of there. So, and finally, let's talk about tag out. So we've all heard about the lockout tagout procedures, and we'll just want to make sure we throw in there that when you secure a machine to do a laser alignment job or to do some kind of corrective work, let's make sure that we follow the correct logout tagout procedures to make sure that while we're working on this machine, somebody doesn't start it up. So let's talk about wireless tools, smart tools that make our jobs faster, easier, and get us in and out before something bad can happen. And then the second part of that is wireless sensors. For years, that's been a big buzz in the industry. Well, now it's actually starting to happen, where we're starting to see these remote wireless tools. So in this example, we see a wireless vibration sensor, and up at the image on the left, you can see this critical motor pump has some wireless sensors mounted. Over on the right, you can see how this works, where the sensors are mounted on the bearings of the machine. It sends that the signal to a gateway. The gateway sends it up to the cloud through Wi-Fi, and then you get the information on your tablet or on your smartphone. On the lower right, you can see a picture of a close-up of this vibration sensor mounted on the bearing of a pump. And then the lower left, you can see an example of a plant where your assets are the black triangles. You can see your critical machines we want to monitor. The red square triangles are the bearings we would monitor on each one of these assets. And then the G's are the gateways. That's where the vibration from these sensors are going to go to the gateways via Bluetooth and then up to the cloud, and now we get the data we need without having to have somebody walk around and collect data. So number one, it reduces the labor, but it also keeps people from having to go out into the space. So let's talk about some example applications where this can save us time, can save us labor, and can be safer. So the first example are hydraulic oil pumps. You know, there's a lot of these oil pumps in a lot of different applications, machine tools, paper plants, power, where you're pumping hydraulics for critical machines. And a lot of times this hydraulic might be at a high temperature, maybe caustic, it may be hard to reach. And so by monitoring these remotely with wireless sensors, we prevent us from getting hurt. Same thing with these belt-driven fans. A lot of these belt-driven fans, the bearings are behind guards and we can't get to them. So the access makes it very tough without shutting the machine down. And this is in almost every application. Every plant you can think of is going to have some type of exhaust or supply fans, and we're having troubles getting to those without removing guards, which makes it unsafe. And so by putting remote sensors in there, we can prevent that safety issue. The same with gearboxes. A lot of times in food and beverage and distribution centers and in mining, you'll have these big gearboxes being driven by big motors that are driving a lot of conveyors. And a lot of these little machines are behind panels that we can't get to, and having sensors on them would allow us to monitor these machines without getting into safety problems. Blowers, a lot of times in water treatment plants, you'll have these big blowers that are very critical. And sometimes we have some environmental concerns because of the raw sewage they're pumping. So if we can use remote sensors and keep us away from a potential health hazard, then that's a good idea. Finally, on this page are blower fans. So way up high on top of blowers in steam plants, we often have these little tiny fans that are very critical. Sometimes they're in high temperature areas, sometimes they're in areas that are hard to get to, or maybe they're not safe. You have to get a ladder. So again, some ideas of where we can use remote vibration sensors. Let's wrap it up with a few more ideas. Food and beverage, medical, and data centers, there are some critical chillers and some critical pumps that could be that the material, it could be ammonia, it could be freon, it could be some material that could be potentially dangerous, and having remote sensors allows us to do that safer. Over on the right, we see some small motor gearboxes that might be hidden behind conveyors in distribution centers or food and beverage that we can't get to, but using remote sensors, we can now safely get to them. And then finally, axial flow fans in manufacturing, pharmaceutical, just about any application where you have these critical, especially in clean room applications, where you can't get in and work on these fans, because if you do, then that means that you've got to shut the room down, and when you do that, then now it's considered dirty and it's not a clean room anymore, and you've got to do a lot of maintenance to clean that room. So a lot of these applications allow us to get into these remote, hazardous, hard to reach areas, and we can do it safely. So let's think about using some of these wireless sensors to let us get data without having to risk a safety situation. Finally, we're going to wrap this up with number 4 and number 5. Number 4 is, let's see if we can use some simple screening tools to be able to identify some problem areas, because catastrophic failure of machines can cause injuries to personnel that are nearby. Sometimes that's going to allow caustic chemicals or biohazard or flammable equipment, or maybe just a health hazard be able to get out. Sometimes it's the secondary damage, maybe it's a smoke, maybe it's a fire, who knows. So by trying to remove faulty equipment, to know about this in advance is a great way to run a plant safer. So the vibration meter is a instrumental tool for that. And so the best way to explain what a vibration meter is it allows us to quickly go in, and without spending an hour at a machine and doing a full diagnosis, we can quickly find out, is the machine good or bad, and then get out of there before we get ourselves into some type of a safety hazard. Because the longer we're next to a rotating machine, the greater the odds something is going to happen. So the best way to explain this tool is like a nurse. Before you go see the doctor, you see a nurse. And the nurse is going to check your blood pressure, pulse, and temperature. And with those 3 pieces of information, the nurse knows whether whether you're healthy or not, because 80%. And so we do the same thing with our machines. This is a nurse for our machine. It takes 3 quick measurements, all within a second. It takes high frequency data for bearings, low frequency for imbalance, misalignment, and looseness, and it also takes a temperature reading. And just like a nurse knows what those numbers mean, we've got a database so that we know, compared to other chillers, for example, whether that vibration level is good or bad. So if we walk around and add this to our operator rounds, they can go in and quickly determine whether the machine is good or bad, because 80% of our machines are good. And if we can quickly find out that machine is good, we don't have to go in there and take that machine down and do a full analysis. We can keep running the machine. If it's bad, then at least now we know that we need to do a test, and we can do it safely on our own schedule. So again, let's spend quick, easy, find out is the machine good or bad, and get out of there before we have some type of a concern. And the last thing we want to talk about here is what about finding problems? So we talked about quickly finding out, is the machine good or bad? Well, once we know whether the machine is good or bad, now we need to find out what the fault is and to fix it. So this is the doctor for our machines. So just like the doctor is going to be able to know, with the vast majority of people that come to the doctor's going to know quickly what the most common problems are. Because when you go see the doctor's going to know that there's only a handful of things that they see every day. Cuts, broken bones, viruses, flus, that kind of things. Well, the same thing with rotating machinery. There are really 4 faults that are the most common for rotating machines: imbalance, misalignment, bearings, and looseness. So just like a doctor, in a short amount of time, we can quickly find out, without bringing in our specialist, what are the most common problems. So in the previous step, we said that 80% of machines are healthy, and we can find it quickly and easily by using a screening tool. Well, the same thing with our common faults. 90% of the faults are common, and we can find that without bringing in a specialist. So why don't we find out what our most common problems are on our most standard machines? And if we can do that in a short amount of time, then we don't have to shut the machine down and bring a specialist in. We still need a specialist on some machines. We're not going to be able to replace a specialist on all machines, but we can use some of these automated tools to supplement our specialist. And so just like a general practice doctor, to take some of the workload, because there aren't enough specialists in the world to do all of our machines. So let's use this tool to be able to diagnose our most common faults. And if it's an easy fault that we can fix ourselves, let's do it. So this final slide that I'm going to talk about here, that kind of brings this all together. So when we talk about making a plant more reliable, making a plant safer to work in, keeping the plant so that we're spending less time in a dangerous work environment. And so there's really 4 steps to this and these can be done without having to call in a specialist or a machine expert, at least on about 90% of the machines in your plant. So we start off way over on the left by using these the stroboscope, or wireless sensors. These are ways that we don't have to walk around our machine and collect data. We can screen our machines from a distance and wirelessly and be able to know whether our machines are good or bad. In some situations, we will use a vibration meter. So all 3 of these tools are screening tools. It all depends on the application and whether it's a remote or a hazardous area to get into. But even if you were to use the vibration meter, which means you do have to touch the bearings of the machine, at least you're only there for a second or 2. Quickly go in, get an answer, and get out of there as quickly and as efficiently as you can. The next step, after you find out which machines are good or bad, are let's find out what the fault is on the majority of the faults and fix it without having to call in an expert. So these automated diagnostic tools are like a general practice doctor, where they're going to find the most common faults: imbalance, misalignment, bearings, and looseness. And those are faults that we can fix ourselves. And also, it's going to tell us how bad it is and when it's time to take the machine down and fix it. So just like a doctor tells us what the problem is, and more importantly, what to do to fix it, that's what this tool does. The next step is let's correct the problem. So after we've seen the nurse and we say, hey, there's something wrong, we've seen the doctor and we find out that we have misalignment and we need to fix the misalignment. Now it's time to go see the surgeon, or it's time to go get an EKG or get some further testing. Again, let's do this with the smallest amount of time and the least amount of impact as we possibly can. We're not going to correct every machine. Let's first screen out and find out which ones have problems. Then let's find out what the problem is, and then let's use the right tool and the right application. Again, quickly go in, fix the correction, fix the problem, get it back to work, and then finally, let's verify to make sure we fix it. So in this diagram, you can see over on the left that on our smartphone, we see that this machine is in the red, and then the diagnostic tool says, hey, you're in the high orange for misalignment. The corrective tool, when we first started, was in the red, and then when we got done, we don't show the screen, but it would be in the green. So we corrected the misalignment. And then over on the right, before we put this machine back in service, we're going to take another quick test with either the vibration tester or the vibration meter, or with the wireless vibration sensor, which will tell us, hey, that machine is healthy, it's time to put it back in line. So those are the steps so that we can quickly, easily fix our machines, keep them from failing and causing safety concerns, and keep us from having to be in harm's way. So this is what we've talked about today. So kind of a summary, we talked about number one, how to be more careful around moving components and how to minimize our time we're next to moving components. Number two, how to work from a distance. We talked about using stroboscopes and infrared thermography cameras as ways to work further away and stay, whenever possible, to have there be some distance between us and the moving parts. Number three, use wireless tools whenever possible, or wireless sensors. So if we can put a wireless sensor on a machine, that means we don't have to walk around and have a technician walk out and maybe get into a safety issue. And then finally, if we can use vibration meters that we can quickly get in and find out is a machine good or bad, the less time we can spend near rotating machines, the better. And then finally, once we get in and take a look at these rotating machines, let's find the problems, fix the problems before we have failures that may cause some either environmental health hazards or some type of a temperature or a caustic material kind of a thing. All right, well, that was our presentation. We've used up just about 30 minutes and we've gone through that. So I think, why don't we open this up to some questions,
Sure.
Nicole?
Thanks, John. If you would just advance one more slide, I think we have information on an offer. Yes, so Fluke is running an offer. I just want to make everyone aware, and we will do so in the follow-up email as well. It's a gift with purchase offer. With purchases over $250, you get free Fluke tools, and I think there's even an iPad in there too. So check that out on our website at transcat.com. Okay, in the meantime, it's time for a Q&A. So as a reminder, if you'd like to ask a question, you can send it through the question box in your webinar controls, which is on the right side. And I'll move on to the first question. Here we go. What can we do to keep from replacing the same bearings and seals time and time again?
Yeah, that's a good question. A lot of people ask that question because when we ask customers, what do you see as your main problems, they're going to say, well, we seem to replace a lot of bearings and seals again and again and again and again. And not only is that a nuisance to the plant and uptime and downtime, it can also be a safety issue. It can be a problem. So what we tell customers is the problem is that we're not finding the root cause and we're not fixing the root cause. Because if you think about it, bearings and seals are a symptom when the root cause is probably misalignment. And so we talked about the alignment tool, and I'm trying to forward to the alignment tool while I'm talking. So if you think about it, the reason that we're fixing the symptom and not the root cause is because in the past alignment has been difficult. And so basically, I mean, I was an electrician in the Navy for 12 years, and we would replace the bearings in the motor. The mechanics would replace the bearings and the seals in the pump, and then 6 months or a year later, we're doing it all over again. And that was because we never really aligned the machine. So we would just kind of eyeball it and put them back in and get them as close as we can. Well, the problem with doing that is that there's a little bit of misalignment that we feel we have to live with. Well, a little bit of misalignment is going to quickly wear your bearings and seals. So if we never fix the root cause, we then just keep on replacing bearings and seals. So what we need to do is we, number one, need to find out what is the problem with our machine, what is the root cause, and that's what vibration testers are designed to do, is they're going to tell us not just that the bearings are bad, it's going to tell us that maybe we have misalignment or maybe we have imbalance. And instead of ignoring imbalance or misalignment because it's too hard to fix, well, replacing bearings and seals isn't just an accepted part of maintenance. We need to fix it. We need to stop replacing bearings and seals. That's too much work. We don't have the time for that. So the answer is find the root cause and then fix the root cause. Don't just keep replacing bearings and seals. Okay, next question.
Oh, okay. Next question. How can we cover hundreds of critical machines with limited resources?
Yeah, so that's a good question because, everybody knows that, there's just way too many machines. And so the simple answer is we want to use screening tools. And so if you think about it, and we kind of talked a little bit about this earlier, think about the medical industry. How does the medical industry, they have the same problem. So if you think about it, there are millions of patients that these specialists have to see, and there's no way that the few medical specialists that we have, the cancer doctors and the brain surgeons, and there's just not enough of these people to go around. So how does the medical industry do it? They do it by screening. So what they first do is they have nurses screen out healthy patients. Then, after when you find out that the patient has a problem, they then send them to a general practice doctor. And before you ever go see the cancer specialist or the brain surgeon, you're going to go see a general practice doctor. And this allows us to screen out a problem at the lowest level and spend a lot less time. We need to do the same thing with our machines. We need to screen out our machines with simple screening tools that take a few seconds, and so that 80% of our machines can, so by looking for the most common problems, by playing the odds, and by fixing the things that are the most common. So instead of starting, so a good example is, if you walk out to your car in the morning and it doesn't start, you don't start by digging into the fuel injectors to see if there's something wrong with the fuel injector. Instead, you start with the simple things. You start with, is there gas? Is the battery have a problem? Do you have a clogged filter of some type? That's the same thing we need to do with our machines. Instead of looking at the tough problems like resonances and excitations and doing these really complicated run-up and coast downs, we need to start with the most common problems first. Number one, is the machine healthy or not? It doesn't make any sense to analyze a healthy machine. We don't want to bring in an expert for a healthy machine. So number one, is the machine healthy or not? And then number two, let's find out if we can fix a common problem before we call in an expert. So that's the way that we do all of our, we do a lot of machines with limited resources. All right, next question.
How can we start a reliability program when we are already 100% busy with PMs and corrective repairs?
Yeah, that's a good question, because, and that's a problem that a lot of customers have. Reliability programs have been around for 30 years or more. I mean, everybody has heard about reliability. Everybody knows it's a good idea. Everybody wants to do it. The problem is, how do we start trending our machines if we're already 100% busy? We're already, in a firefighter mode where we're having to run around and, we're so busy with our PMs and so busy with fixing machines that we just don't have time to start trending. So the way that some customers have found to be successful is a simple idea of start small and grow. So what they do is, instead of trying to set up a big program on 5,000 machines right off the beginning, which never works out, that's one of the biggest killers to a new program, is trying to do all your machines at once. You'll never get started, because in 3 months, when the CEO or upper management says, how's that reliability program going? You're going to say, oh, we haven't even done anything yet. Well, so what you have to do is you have to start with like 20 or 25 machines. And so just start off with a small group of machines, maybe a pilot program, maybe just a small portion, and start doing a few machines. And when you start doing those machines, you start finding some successes. When you start finding some successes, then you can start waving the flag and you can start getting some buy-in and some time. In addition, when you start getting some successes on a few machines, you'll also find out that you have a little bit extra time. Why? Because you're doing fewer PMs and you're doing fewer corrective actions. So if I start with a few machines and get myself a little bit of time, now I can do a few more machines. So every month, do a few more machines, and this thing will get bigger and bigger until next thing you know, in a year or two, now you're trending your machines instead of doing unnecessary PMs or unnecessary corrective actions. But it all starts out by taking little baby steps first and then growing the program.
Okay. Is there a way of integrating Fluke's wireless sensor output into an automated system using something like 4 to 20 milliamps or 0 to 10 volts?
Yes, and I'm not the expert in that, and so we might have to get you some more information on that. But yes, that is what the Fluke Connect program was designed to do. A couple of years ago, a lot of our customers were saying, it sure would be nice if you could take data from all of your tools and bring it together. And so what we started to do is we build these tools that have these this Bluetooth or Wi-Fi sensors in them, so that we take the data from the tool, whether it be like an 805 vibration meter or a 3561 wireless sensor, or from a thermal tool. There are 40 or 50 different Fluke tools, maybe more, that have this wireless radio built into them, so that the results from this tool, instead of being locked into a tool or locked into a program, now can get up into the cloud, and now we can integrate all of these results into one common software platform. Not only is it important that we're now putting all this information together in one place, but now we can push this information out to the right people. So now we can share this data, number one, with experts, number two, with managers. So now the technicians, the managers, the experts, the planners, the programmers all of these people are now talking are getting the answers, and not just data. What we don't want to do is just have reams and reams of data going up into the cloud. What we want to do is be able to get answers from that data and then integrate the answers so that planners and managers have the answers that they need to start making work orders and start making good decisions on maintenance practices.
Okay.
All right, thanks.
Last question, unless anyone submits one in the meantime, is what vibration tools should we begin with?
Yeah, so that's a great question, and a lot of people ask that. And my answer is always start small and grow. Start with a screening tool and work your way up. So just like when you think about the example I talked about earlier about using the car, working on your car. The first tool that you want to get when you're working on a car isn't going to be something that would help you work on the fuel injectors. It's going to be a tool that's going to help you quickly find out what's wrong with the machine. So for a rotating machine, we don't want to start with a high-end real-time vibration analyzer that an expert would take months to learn how to use and years to learn how to use and get the experience. We want to start with simple screening tools. So things that our technicians and operators can learn in 30 minutes or less to be able to go out and quickly start getting. We want to find out, first of all, which machines are good or bad. The good news is those tools are a couple of $1,000s instead of $50,000. If you think about a high-end vibration analyzer, the training and experience it takes, by the time you get done, you've dropped $50,000. Let's start with simple tools. So I would say that you would want a simple vibration screening tool, a simple thermography screening tool, and a simple electrical screening tool. Instead of starting with just one high-end vibration or one high-end thermography tool, start with 3 small, easy, cheap, simple to use screening tools and have your people start, because there isn't one tool that can do all in the plant. A high-end thermal camera isn't going to do everything you need in the plant. A high-end vibration analyzer isn't going to do everything you need to do in a plant. A high-end electrical tool isn't going to do everything you need in a plant. So you need thermography, you need vibration, and you need electrical. And so I would say start with a screening tool of each one of those, and that's the best way to start a program.
Okay, thank you. That concludes our time today. If you do have further questions that weren't answered or would like to find out more about what Transcat offers product and service-wise, you can contact us at 800-800-5001 on the web at transcat.com, or you can email me directly at nvanword@transcat.com, and I'll get you answers. I appreciate you joining us today. We hope you got something out of the presentation and that you continue to join us for future Transcat e-learning webinars. Thank you, John.
Thank you, Nicole. See you.
Take care.
Bye.